Uh, Hi everyone, I'm Ying from Peking University. I'm very happy to be here presenting our work, The Surprising Benefits of Basically Neglect in Robust Aggregation. This is a joint work with Yuqing from Peking University and Wang from Tsinghua University. Yuqing is my advisor. So let's start. Imagine you are an investor and your friend has recommended a startup project named Neuralink AI to you, and you are now deciding whether or not to invest in this project. If you don't invest, then nothing happens. If you choose to invest, you will get some share, and you will get a big fortune of money if the project succeeds. However, if the project fails, you will get nothing and lose all the money you put in. As a rational investor, you know that whether to invest depends on the probability of its succeeding. However, as a layperson, you know nothing about projects, so the only thing you can do is to ask experts. If you can ask only one expert, then a perfect Bayesian machine is a better choice comparing to a human expert who have the same prior information. This is because human can make mistakes. So before we go further, we will give an example of human human error. So let's see, Mark's company has advanced technology and their first generation production has been widely accepted by market. Do you think his company will go public with a high probability? So who think the company will go public? Who think no? Okay, thank you. Let's see the context. The company has advanced technology. The product is widely accepted. These are all positive signals. So your intuition tells you that, oh, the company has a promising future and they will finally go public. But the answer is no, because only a small ratio of companies can finally go public. Such an error is basically neglect. It is a common cognitive bias of human beings that say we tend to ignore the base rate and focus on the feature information when we are making predictions. So let's go back to our story. But this time we can ask two experts with different prior information. Things become more complex because we need to first decide who to ask and then consider how to aggregate their individual predictions. So here is the question. If we can ask two experts, should we turn to the perfect Bayesian machines, or we just ask two human experts? Surprisingly, our results shows that in some conditions, it is better to turn to human experts. So this is an overview of our talk. I will start by the modeling thing, and I will talk about how to evaluate the aggregator, and next is our main results. We are aiming for the succeeding probability of a startup project, and we can ask two experts. These experts each will receive signals of the project independently and make predictions based on their private signals. We can only see these experts' predictions, and we need to aggregate them into a final estimation. We highlight that in this model, we do not see experts' private signals, and we do not know the underlying information structure, which is a joint distribution between the project's success and expert signals. The only assumption here is that expert signals are conditionally independent given the project's outcome. Then we talk about how individual experts make his prediction. So now we imagine, so just forget previous thing. Imagine you are a technical expert and you know that among all the projects in the market, only 15% of them will finally succeed. From your technical view, you know the project can be divided into two types: the project with advanced tech and the project with regular tech. And you know that among those successful projects, about 80% of them has advanced tech, while among those failed projects, only 20% of them has advanced tech, and the remaining 80% has regular tech. Given all this background information, you see that the current project has advanced technology. Then what is its probability of success? Well, different experts will give different answers. So here Snoopy say it's 80%, Charlie say it's 63%, and Robot say it's 41%. Let's see how they make these predictions. So the robots give a Bayesian posterior based on the Bayesian rules. And Snoopy say it's 80% because it totally ignores the base rate of success. And Charlie provides some answer between these two answers because it partially considers the base rate when he's making prediction. We use this base rate neglect model to formally describe how experts make their predictions. So here we use mu to denote the base rate of success, and there is a parameter lambda. It controls how much the individual experts consider the base rate in their predictions. When lambda is 0, the experts totally ignore the base rate thing and make a perfect base rate neglect response. And when lambda is equal to 1, the experts will provide a perfect Bayesian prediction. In our previous example, Charlie corresponding to experts with lambda equals to 0.5. And our results show that if we ask experts with some middle level lambda, we will get the most accurate final prediction. To make things clear, we need to formally define what is the accuracy or inaccuracy of the final prediction, and we need to talk about how to evaluate the performance of the aggregators. Notice that the accuracy of your final prediction does not only depend on who you ask, it also depends on how you aggregate, and it depends on the unknown information structure. So here we use a 2-to-1 mapping to denote how we aggregate the predictions. There is an aggregator, and to measure the inaccuracy of the aggregator on some unknown information structures, we adopt the robust framework in previous work. So we define the regret of the aggregator at some degree as the maximum difference between the loss of our final prediction and the loss of the optimal prediction, where the optimal prediction is made by an all-knowing expert with the knowledge of the underlying information structure and individual expert signals. The parameter lambda here control how much the individual consider the base rate in their predictions. Okay, I think everything's clear. Let's go to the main results part. So our main theorem shows that the regret curve of any aggregator are single troughed. That is, the regret is either monotone or first decrease and then increase as the base rate consideration degree lambda increase from 0 to 1. We visualize this result as this graph. So, sorry. So in our numerical results, we find many aggregators have non-monotone regret. So the regret curve actually forms street V shape. For example, the average prior aggregator, which is designed for a perfect Bayesian expert, has a small regret when lambda is smaller than 1. This shows that with 2 experts with Bayesian neglect, we can get more accurate final prediction. In addition, we find our proposed aggregator achieves an almost 0 regret at lambda equal to 0.5. This means that we can almost perfectly recover the annoying experts posterior. And this regret is much lower than the regret lower bound at lambda equals to 1, indicating that with Bayes' neglect, we can achieve better aggregation than any aggregator with Bayesian input. We also do empirical study to collect human prediction data and empirically test the performance of the aggregators. So we use the standard belief updating task and strategy method to elicit the forecast of humans. Human in a broad set of information structure. We find there is a gap between our theory and our experiment. For example, over half of the human prediction are out of our theoretical model. But still, we find Bayes' neglect has some smaller regret. Due to the time limit, I will skip this part, but we do recommend you to refer to the full paper. We just go into the related work part. So forecast aggregation is widely studied. A number of work consider this aggregation problem in a robust framework where the performance of the aggregator is measured by the worst case among a set of possible information structures. While most of these previous work consider the Bayesian expert, our work consider a non-Bayesian influence of human. That is Bayes' neglect. It is a common error widely observed and studied in the literature of economics and psychology. And our work reviews the positive impact of Bayes' neglect in a robust aggregation setting. So we try to provide some intuition for our findings. In this problem, there are 3 types of information. The base rate information, which is public to both experts, and 2 experts' private signals. If the experts are Bayesian, then each of them will consider the public information and their private signal in a 1-to-1 ratio when they are making predictions. However, since the aggregator do not know the underlying information structure, it cannot differentiate the public information and the private information when we aggregate the predictions. So this results in an overemphasize of the public base rate information. But if the experts each underweight the base rate information in their prediction, we can get a better aggregation because we can balance the informations better. So to take away a certain degree of base rate neglect helps robust aggregation. You don't need to spend a lot on training machine to provide Bayesian predictions. Human experts who will make mistakes can help you better. We thank Tracy Liu for her valuable comments in the empirical part. And we also thank Yuqing and Zhihuan for their sharing code, which helps in the initial stage of this study. Okay. I think that's all.